So based on that simulation, let's talk about the properties of our sampling distribution of proportions. So in terms of what will be given in the problems, we'll be given some population proportion, or it could even be just a proportion that we expect to occur, and we'll be given some sample size that we're going to look at. Then with those two pieces, we can form the rest. So making our sampling distribution, the first thing we'll need to do is check the central limit theorem. So something that we just discussed in the simulation was how important sample size is in order to make sure that we have a bell-shaped curve, because that's where we want to end up here, is through these steps we want to end up with a bell-shaped curve that we can calculate things with. So to do that, the first thing we need to do is check the central limit theorem. And that's listed at the bottom here in this box. So the normal model is an appropriate approximation for a sampling distribution of proportions if the following conditions hold. So independence is that the individuals in the sample whose proportion we're finding must be independent of each other. So like rolling a die was independent, flipping a coin is independent, those probabilities aren't changing. Sampling people, typically if we have randomness, that'll imply independence a bit. Or what we can use is this fact that sampling less than 10% of the population. So if we're talking about like out of all Americans and we sample 100 people, that's less than 10% of the population, so we can assume independence. So what we want to do is make sure that we have independence in some form. Randomization, we should have randomness, and then also, if they don't specifically say it's random, sometimes we're just going to assume that it's random to move forward with the problem. So we should have some sort of randomness to the selection of our sample. And then the piece where we need to show work is with success-failure condition. And that's where we'll take our sample size times our population proportion and make sure that's more than or equal to 10. And then we'll also take our sample size times 1 minus that population proportion. So Q is just 1 minus P, and make sure that that's also more than or equal to 10. So they both have to be more than or equal to 10 for us to pass that success-failure condition. So then from there, what we're going to do is build our normal distribution. So building the normal distribution, what we need to know is what is the center and spread. So if we have this random variable, which in this case is representing a sample proportion, if we check the central limit theorem, then we know it's normally distributed. But then what we need to know is what is the mean and what is the standard deviation. So for the mean, what we talked about in the previous video was how this mean of our sample proportion, or this average of sample proportions, same thing, is just going to equal your population proportion. When we take these samples, they're going to center around that population proportion because that's what's expected for our samples. So for the center of this distribution, you're just going to use your population proportion. These pieces here, defining the mean and defining the standard deviation, you might see terminology that says define the parameters, and that's what we're doing here. The parameters is this population mean and population standard deviation. So to define the mean, you would just write in the population proportion. And then for standard deviation, I said there would be a formula for it, and it is right here. So the standard deviation of sample proportions. And you can write it either way with the population standard deviation symbol with the subscript of p hat works, or SD of p hat, same thing. What we'll be taking is this square root of p times q over n. So to get our standard deviation, we'll have this calculation to do of p times q over our sample size, all under the square root together. So with those two pieces, we'd have this distribution of samples so that if I need to find any information about a single sample that we take from sample size n, then we can talk about probability, or we could start doing percentiles. We use any of those tools that we did for the normal distribution. So let's see how this works in an example. Suppose 60% of all college students are either very satisfied or completely satisfied with their online shopping experience. You decide to take a nationwide random sample of 2,500 college students and ask if they agree. So this first question here, is it reasonable to use a normal model for the sampling distribution? So this idea of, is it appropriate to use a normal model? This is getting at, do we pass the central limit theorem? That's our test for whether or not we have a bell-shaped curve. So we need to think about three things. We need to think about independence, randomization, and success failure. So, first, let's look through the pieces that we have here. So what they tell us is, suppose 60% of all college students are either very satisfied or completely satisfied. So 60% of all, they're giving us a population proportion. So there's our population proportion, 60%. Then the other piece that's going to be important to us is that they take a random sample of 2,500 college students. So that right there is our sample size. So it'll give us our population proportion and sample size. So independence, when it's going to be sampling people, the easiest way to think about it is that 10% condition. So 2,500 college students, that's less than 10% of all college students. I'm not going to ask you to write an explanation here, but that would be what I would write out. Really, I just want to know that you thought about, like, is there independence here? Are there answers influencing each other? Which, no, there isn't. So just write down independence with a little check mark to show you thought about it, and we're good to go. Randomization, we'll have that because they say it's a random sample, so we're all good there. And then success failure, this is where we'll show a little bit of work. So I'm going to take 2,500 times that population proportion of 0.6. I'm also going to take 2,500 times 1 minus 0.6, which is a 0.4. And what I should see is that both of those are at least 10. So the first one will be 1,500. That's more than or equal to 10, so we're good there. And then the other is 1,000, which that's also more than or equal to 10, so we're all good there. So we pass all three conditions for the central limit theorem. So is it reasonable to use a normal model? Yes, because we pass that central limit theorem. Again, as soon as one piece fails, then we can't do any of this. We would be stuck. So find the mean and standard deviation of the proportion of survey respondents who agree. So mean and standard deviation of the proportion. So that notation comes through mean of the proportion, standard deviation of the proportion. So mean of the proportion, there's no work to do here. All you have to do is copy down that population proportion, which was at 60%. And then we'll want to use the decimal form here in the calculations, so that'll be a 0.6. So with the mean of these distribution, I always just think like easy peasy, you're just copying. Standard deviation, however, has a calculation to do. So we want to use this square root of p times q over n. So what I need to do is take a big square root, and we're going to take 0.6 times q, which would be 0.4, over our sample size of 2,500. So put that in a calculator and we should get a 0.0098. So now with these pieces, we pass the central limit theorem. We know the mean, we know the standard deviation. We can start to think about our normal distribution. So we know it's normal from that first part there, and then now we know numbers to plug in because of the mean and standard deviation. So then we can start answering questions involving probability. So, what's the probability that the sample proportion of the 2,500 college students who agree is at least 57%? So, what we're doing here is we want to see what's the probability of having this value of p hat, or rather at least that value of p hat, given our sample size of 2,500, given that we expect this population proportion of 0.6 coming through. So what we need is our distribution. So this bell-shaped curve that we're building here is going to show us how these proportions distribute, this sample proportion of 2,500 college students, and agreeing based on that we expect 0.6. So I could already draw the center there. I know that's going to be 0.6. If I wanted to, I'm just going to round this a little bit for ease, but I could start to make a number line here. I'm just going to round the standard deviation to 0.01. So like this would be 0.61, this would be 0.62, this would be a 0.59, this would be a 0.58. So then what I get here is the idea of how these samples would distribute. Taking a random sample of 2,500 college students, expecting 60% to agree based on that data that they have from the population. That's what we would expect from a random sample. But again, with these random samples, we should have a little bit of variability of going above, below, and then it's just a matter of what the standard deviation is. So like taking a sample of 2,500 and seeing 61% agree, not that unlikely. But as soon as I start going on to these regions beyond 62%, beyond 58%, then that starts to become pretty unlikely. And something you might be noticing here, like when we first read this question, looking for this 57%, that is pretty close to 60%. But as you can see on this graph here, by doing this calculation, we can see actually that's pretty unlikely. 57% is all the way out here. So that's kind of an extreme value to get from a sample randomly. And where that's coming in is it's really the sample size having an effect. You can see it coming through in the actual calculation. Like the numerator there, P and Q are going to be set based on the population data. What you're going to see changing is sample size. And in this case, we have a big sample size. And when we have a large sample size, as we talked about before, that means we really expect 60% to come through. We don't expect to have that much variability because we have such a large sample size. So that's where these numbers end up being pretty close by, and this idea of having a really low standard deviation, we really expect to be in this region around 60%. All right, so to get back to the actual question that we're asking, is we want to know what's the probability. So we want to find area under the curve of at least 57%. So what I want to do here is find at least that value. So that's going to be at or more than 57%. So then this becomes a GeoGebra problem, or whatever technology you're using. So what I need to do is go to GeoGebra, and there I'm going to use this mean of 0.6 and standard deviation of 0.0098. So 0.6, 0.0098. And then we can see my number line there, 0.6, where it's expected, and I can see how it lines up with how I drew the picture. And then I want this probability of at least 0.57. So I want my line to start at 0.57 and shade to the right. So this will be right-tailed. And then I'm just going to change that to a 0.57. So this probability of being at least 0.57, and because we shaded such a large region, we expect a high probability, and we're getting that with this 0.9989. So within GeoGebra, we got that this probability of seeing at least 0.57 is a 0.9989. So now making our sentence, and this can be kind of a tricky part here because we have a lot of percentages going around here. Something to take note of is a proportion. It's a percent of a sample. So like this 57% that's coming through, it's like this 57% of 2,500 college students. This probability that we're getting out, this 99.89, this is a percent chance. So we have these percentages coming through, but when it's a proportion, it's a percent of a group. And then with probability, it's this percent chance or percent probability. So making my sentence, I'm going to kind of follow how I was making sentences before, is I'm going to start with the probability. I'm just going to say there is a 99.89% chance that, and then I'm just going to recycle some of the wording up there. In fact, I'm just going to start kind of copying that the sample proportion of the 2,500 college students who agree is at least 57%. So with the sentences where students might kind of feel uncomfortable is that we have two percentages, but just keep in mind one is describing the actual probability of the event and the other is describing this proportion of the group. So seeing this 57% agree of that sample size. All right, we'll have one more video with another example for you, but that's the overall properties and then how we're going to be using our sampling distribution of proportions.